Good afternoon, everybody. First of all, I would like to thank the organizers to give me the opportunity to make this talk. This work presented today is a part of the PhD work of my student Alexandre Morvan, supervised by Professor Angela Vela and me, and with the help of Dr. Nicolas Delpouve. This work has been performed in the GPM laboratory situated in Rouen, near Paris, as shown here. Rouen is a very touristic town and well known for the international event called the Armada. The GPM laboratory, it is approximately 170 persons with more or less 60 PhD students per year. This laboratory is divided in 5 departments, and I work in the department called Disorder Systems and Polymers. In these departments, we try to correlate the microstructure and the properties of polymers and nanocomposites, and we try to understand the structural relaxation phenomena in glass-forming liquids, and to follow the evolution of this relaxation phenomena as the function of time, temperature, and frequency. To illustrate the glass forming ability, we can use this Enthalpic diagram. When a liquid is cooled fast enough to avoid the crystallization, we'll reach the liquid-like state, and at a certain temperature called the glass transition temperature, noted Tg here, we form a glass. A glass is out of equilibrium, and the equilibrium state corresponds, in fact, to the dotted line here, which corresponds to the extrapolated curve of the liquid-like state. Thus, as a glass has a certain molecular mobility and is out of equilibrium, if we maintain the glass at a temperature below the glass transition temperature, it will try to lose its excess of enthalpy to reach the equilibrium state. This natural phenomenon is called the physical aging, and this physical aging modifies the physical properties of a glass. And it is important to precise that the signature of the heating after the aging is characteristic of the molecular mobility in the glassy state. The physical aging can be easily characterized by calorimetric investigations. This is the typical signature of a glass just formed or rejuvenated. And now, in green on these curves, we have the signature of the same glass, but after a certain aging duration. To quantify the enthalpy loss for a given aging duration, noted TA, we use this equation where CPA corresponds to the curve of an aged system and CPR to the rejuvenated system. And experimentally, we estimate the enthalpy loss, and this quantity is directly compared to delta H infinite. But the way by which a glass reaches or not its equilibrium state after a very long aging time is still a matter of debate in the scientific community. I can, for example, mention these very recent papers from 2018 up to 2020 about these topics. More particularly, I would like to mention the work of Daniele Cangallosi, published in Physical Review Letter, which evidenced 2 equilibrium mechanisms during the physical aging, by highlighting an intermediate plateau here. I would like also to mention this recent paper of René Androche, which explains, in fact, the possibility to crystallize after the physical aging if the time is long enough. So our goal was to better understand the mechanism involved during the physical aging process. To do that, we have chosen the selenium glass, considered as an excellent glass former with high degree of purity and with a very simple structure. And for this goal, we have combined two different experimental techniques, the differential scanning calorimetry and the fast scanning calorimetry. So what about the fast scanning calorimetry? As shown here, the sample is placed directly in a sensor corresponding to the oven. The mass of the sample is around few nanograms, and we have shown that this technique offers the possibility to accelerate the physical aging process and thus to analyze this process in the laboratory timescale. To illustrate this, I propose to show you an example of aging study with amorphous PLA. These are the experimental curves obtained by the FSC technique for an aging temperature 13 degrees C below the glass transition temperature and for cooling and heating rates of 1500 Kelvin per second. From these curves, we estimated the enthalpy recovery, and as you can see here, we reached the plateau corresponding to the equilibrium state in 100 minutes. By comparison, we will need approximately 200 years for the same thing by classical DSC. So FSC offers the possibility to accelerate the physical aging process. So now, what about the physical aging process in selenium glass? First, we started by classical DSC investigations with sample aged from 10 hours up to 40 years at, in fact, 17 degrees C. These are the experimental curve that we have obtained and the enthalpy loss that we have calculated. We can observe that the delta Cp values are identical between aged samples and rejuvenated ones, so the physical aging is reversible. We observe that the selenium aged during 20, 30, and 40 years exhibits an enthalpy of recovery equal to the theoretical maximum enthalpy, noted delta H infinite. It is presented here. So we can conclude that the samples have reached the equilibrium state and are stable in time for an aging at 17 degrees C. After this, we performed fast scanning calorimetry investigations on the selenium glass. The samples are aged 10 minutes at different aging temperatures. We observe this kind of experimental curves, and for each aging temperature, we calculate the enthalpy of recovery. As you can observe here, the equilibrium is reached for aging performed during 10 minutes at temperatures higher than 30 degrees C, and for aging temperatures between 60 and 26 degrees C, the enthalpy of recovery decreases with the decrease of the aging temperature. So, what can explain this change of behavior at a certain aging temperature? To try to find an answer, we perform aging far from Tg. Tg is equal to 40 degrees C for selenium glass. And we perform also aging close to Tg. Here we have the experimental curves obtained for Ta equal to 17 degrees C, and for TA equal to 35 degrees C. So here, far from TG, and here, close to TG. We clearly observe different relaxation mechanisms. As shown here, for TA far from TG, we have an intermediate plateau, and for TA close to TG, we reach the equilibrium state in only one step. So we evidence different mechanisms of relaxation depending on the gap between TG and TA. And these results are in good agreement with the predictions of Congalozzi et al. So now, what about the physical aging process beyond the thermodynamic equilibrium? We perform new FSC investigations at aging temperature of 35 degrees C with different aging time. At a certain aging duration, we observe a cold crystallization peaks during the heating scan after the aging. So for this temperature, we have a cold crystallization which appears, and this cold crystallization observed during the heating scan is in fact a consequence of the nucleation occurring once the equilibrium is reached after aging, as proposed by René Androche et al. Always for understanding what happens beyond the thermodynamic equilibrium, we perform the same kind of experiments, but by changing the aging temperature. We choose TA equal to 31 degrees C. And for this aging temperature, a second endothermic peak is observed during the heating scan after the aging duration. This second endothermic peak corresponds to the melt of crystalline phase generated once the sample reaches the equilibrium state. And we can say that for this temperature, when the equilibrium is reached, additional ordering proceeds that progressively leads to a crystal growth. So we can conclude that, depending on time temperature conditions, it exists a window where the mobility is sufficiently high for allowing the nucleation formation, but sufficiently low to allow the crystal growth. Finally, we compare the aging kinetics between differential scanning calorimetry and fast scanning calorimetry experiments. For this goal, we have in fact two ways of comparison. Indeed, we can work at equivalent aging temperature. So in our case, we choose 17 degrees C at aging temperature for the two kind of experiments. So we have to compare the red square, and the purple cycles on this graph. But we can also work at equivalent distance from the equilibrium. It means that in this case, we have the same value for delta H infinite. And for this comparison, we have to compare, in fact, the gray squares and the purple cycles. So, as you can see here, at equivalent aging temperature of 17 degrees C, by FSC we need approximately 300 hours to reach the equilibrium state instead of 13 years by classical DSC. And if we work at equivalent distance from the equilibrium, we need approximately 100 hours to reach the equilibrium state by FSC instead of 13 years by classical DSC. So it is clear that the physical aging is accelerated by FSC. So now, to conclude, we can say that thanks to calorimetric investigations, so performed by classical DAC and fast scanning calorimetry measurements, we evidence different relaxation mechanisms occurring during the physical aging process, and this mechanism depends clearly on the gap between the glass transition temperature and the aging temperature. We evidence also that the crystallization process is possible when the equilibrium is reached and if the relaxing entities have enough mobility. We also prove that the physical aging is accelerated by the fast scanning calorimetry measurements. So if you are interested by this work, all these results have been recently published in this paper. And I would like to thank you for your attention.